The next constellation is Cassiopeia, and in Cassiopeia, which is a northern circumpolar constellation, we have two historic supernovas, Cas A and Tycho. Cas A is a type 2 supernova event. It is the core collapse of a massive star. It ran out of hydrogen fuel in its core, fusion stopped, so it started to collapse, it started to fuse helium, and then it ran out of helium, and then it started fusing heavier and heavier atomic nuclei up until iron and some nickel. When you fuse iron, then the ball game changes, because up until then, every fusion product was exothermic. It produced energy which provided the radiation pressure, which held gravity at bay. However, once you start fusing iron, you have a problem because iron is exothermic. It absorbs every piece of energy it can find, and it immediately takes all the energy away. There's no more pressure out to counteract the gravity in, and so we have a catastrophic, instantaneous collapse of the star. So that is a type 2 event, the core collapse of a massive star. When that happens, unlike the planetary nebula and white dwarf, which is pretty kind of wimpy little core rebound for that one, this one is enormous. There is so much mass in these stars, and Cas A was probably between 20 and 30 solar masses, so much more mass that when that core rebounds, it rebounds, and it meets that infalling material, and it just throws it out into the interstellar medium in these beautiful supernova remnants that we see. The rest of the star, that's only about 5% of the star that we actually see in the remnant. About 95% of that star ends up in the core. And the core for this type of a star is not a white dwarf, because electron degeneracy pressure, electron against electron, is no longer strong enough to stop gravity. So when it contracts and collapses, the electrons are shoved right inside the nuclei of the atoms, where they combine with the protons and form neutrons. So now we have neutron degeneracy pressure holding this stellar core, this neutron star, in equilibrium. Neutron pressure out, gravity in. However, Tycho is a totally different ballgame. If you have a white dwarf, and that white dwarf is has a companion star. Most stars out there, 2/3 of all stars, are in binary and multiple star systems. So this is more common than a solitary star like the sun. So if you have a white dwarf, which obviously is a star that started out a sun-sized star, evolved through all its stages, left a little white dwarf behind, but has a companion. And that companion now, which was a little less massive, now it starts evolving, and it goes through its evolutionary sequence and becomes a red giant. Well, now we have a red giant with very loosely held outer atmospheric material, and we have right next door a white dwarf with an exceedingly strong gravitational field. So if these two objects are close enough that contact can be made, then the white dwarf can accrete material away from the surface of the white dwarf from the atmospheric material of the red giant, and it forms an accretion disk around the white dwarf. So we have red giant, material transfer, accretion disk, white dwarf. If every now and then a little bit of material dumps onto the surface of the white dwarf, we have a nova. If at some point, because this is a very, very unstable system, and a whole mass of material dumps onto the surface of the white dwarf so that it approaches Chandrasekhar's limit of about 1.4 solar masses, then you have a runaway fusion event that starts in the core of the white dwarf and literally blows the white dwarf up. So you have now a supernova remnant with no stellar core. All remnant, no core. That is a type 1a supernova event, and that is what Tycho is. In Cygnus, there is Deneb, class A star, luminosity 1, which tells you Deneb has evolved off the main sequence on its way towards its future evolutionary history. Within this constellation, we have Cygnus X1, which is a stellar mass black hole. It's about 15 solar masses, and it has a companion, a massive B classification companion that is still on the main sequence. And what happens when a black hole forms is that when you're undergoing that massive collapse for a type 2 supernova event, there is so much more mass on these stars, and it has to be more than 24. I hate using numbers in astronomy. I always get in trouble when I do because everybody has a different number. But something like 24 to 30 solar masses, it can become a black hole, because with that much mass behind the core collapse, that the neutron stars can no longer counteract the gravity, not strong enough. So that's the strongest force we know, the strong nuclear force. It cannot stop gravity. So the neutrons are shoved right inside the neutrons, and that just keeps happening until what we have is a mathematical point called a black hole. And this one is a 15 solar mass one. And other than that, that's all we know, all you need to know about black holes for this particular competition. So, Dorado. Dorado is a constellation in the southern hemisphere. It includes Large Magellanic Cloud. Large Magellanic Cloud is part of the local group of galaxies that includes the Milky Way, the Andromeda Galaxy, large and small Magellanic Clouds, and they're, you hear different numbers, 50, 57, 50-something galaxies in the local group. Most of them are just small, irregular galaxies with very little structure. And this is what they look like from the southern hemisphere. They're easily observable in the night sky in the southern hemisphere. And the Large Magellanic Cloud is 160,000 light years away. The Small Magellanic Cloud, which you can see above the large one, the smaller one is about 200,000 light years away. And this is an amazing image of the Large Magellanic Cloud. The image on the left is from a survey, the Magellanic Cloud Emission Line Survey, that was put together by a group of students at the University of Michigan working with the Cerro Tololo Telescope Observatory in Chile. This is actually a composite of 1,500 separate images that they put together, and it shows all of the round things that you see, the roundish structures. Those are all supernova remnants. And the places that look kind of dark with nothing there is where they've carved out and photo-evaporated away the clouds of gas and dust that are have been being used up in forming of new stars. This is actually and the 30 Doradus, the Tarantula Nebula, which is a star formation region within the Large Magellanic Cloud, is actually the largest and most complex star formation region in the entire galactic neighborhood. So it is massive.